Okay, so now we're going to take a slightly different look at Faraday's law of induction, and this time we're going to look at it from the microscopic view of the charge carrier. We can imagine we have a piece of conducting material right here. We have a little piece of metal, whatever, and there are electrons within it, and we're going to apply a force to this metal, and we're going to move it through this magnetic field. Now, the magnetic field points into the board. The electrons, negative charge carriers, will feel a force in the opposite direction of the right-hand rule, and our velocity goes this way. Now, for positive charges, right-hand rule applies. If we have positive charges here, V cross B would tell us that the force would be upward. We have negative charges, so the force is in the opposite direction. The result would be the same. But we have negative charges building up at the very bottom of this, positive charges building up here. We are moving this conductor through a magnetic field. We are building up an EMF. Positive voltage up here, negative voltage down there. There's your potential difference. Okay, so let's now take this and connect it to create a circuit. Okay, I'm going to connect this to some type of load, and maybe it'll just have a small resistor right here. And we're going to do the same thing we did before and try to figure out what goes on. Once again, here's our metal, same as before. As we push it in this particular direction, the electrons feel a force and they're pushed downward. Now, for every action, there's an equal and opposite reaction. That's Newton's third law. So as we pull it this way and the electrons are forced down, okay, there will be an opposing force in the opposite direction. And this makes sense because we have to do work on this. We have to apply work here. And as we put mechanical energy into the system, that is converted into electrical energy, and that creates the current that flows through here. Okay? So again, V cross B tells us that the electrons are going to move downward. That is going to create the potential difference, causing the current to go, in this case, in a counterclockwise direction and pass through the resistor. Another way of looking at this is almost seeing it in terms of Faraday's law. We'll go back to this right here. As we move it this way, if we now have connected it to a circuit, the circuit is basically enclosing this much of the magnetic field, basically surrounding the magnetic flux. As the bar moves to the right, the magnetic flux increases because we're encircling a larger number of field lines. Okay? So by the simple force is equal to Q V cross B, we see that we are going to get an electric potential. By Faraday's law, it's just another way of looking at the same phenomena, but looking at it in terms of how much magnetic flux we're encompassing. Okay? So both give us the same result. And again, the EMF is equal to BL times V. B is our magnetic field. L is the length of this conductor as it moves down these rails. And V is equal to the velocity. Now remember, velocity is delta x over delta t, or if you want to use a more general form, dx dt. Okay? So this area is getting bigger by delta x times L. Okay? The rate at which it gets bigger is delta x over delta t times L, or L times V. So what we see here is just another version of Faraday's law of induction. E is equal to the change in magnetic flux as a function of the change in time. The magnetic flux is B times A. Okay, B is constant, so that can go out front. A is equal to L times L times delta x, and we replace delta x with V is equal to delta x over t, and that gives you the rate of time. So again, we're getting the same result as we got with Faraday's law by looking at the microscopic charge and seeing how it behaves. Again, conservation of energy applies here. So the force times the distance that I move it in this direction, the work that I put into it, is going to be equal to the energy that I get into the system. So as I pull in this direction, there's going to be an opposing or resistive magnetic force, okay, which is going to convert the work that I put into it into electrical energy. Okay? So again, I put mechanical energy into this, all right? The magnetic field converts the mechanical energy into electrical energy, and that's basically how the induction works. Once again, EMF is equal to BL times V. The faster that this bar is moving, the more potential that I set up right here. By Ohm's law, V equals IR. We also know that the current, therefore, is equal to V divided by R. V is the electromotive force. So I can make that substitution right here. And I get that the current is equal to B, the strength of magnetic field, times L, the length of this wire right here. So a bigger wire is going to give me more current. V, the faster that I move this, the more current I'm going to get to flow. And then divided by R, the resistance. Now, when we're creating a electrical generator, when we want to take mechanical energy, work in this case, and convert it into electrical energy, the previous setup that we had really doesn't make a lot of sense. Going back to this right here, we could only move this bar so far before we'd run out of room. We can actually do a reciprocal type of motion back and forth and generate AC electricity. But for most practical purposes, doing work that way just is a little bit cumbersome. Okay? But again, we can clearly see you change the magnetic flux through this loop, you're going to induce an EMF, and we can see how the forces act on the charges. Instead of having a loop of current and changing the magnetic flux through that, okay, most generators can get that change in magnetic flux rather than changing the overall area, rather change the orientation. Remember earlier when we looked at Faraday's law of induction and we used the more specific form, which said that the magnetic flux was equal to BA times cosine theta. And therefore, if we're calculating the rate that the magnetic flux is changing, we can simply change the magnetic field, we could change the area, we can change the orientation. Most generators will change that magnetic flux by simply rotating a loop of wire or several loops of wire within the magnetic field, and that will put a force on the charge carriers, the electrons on the loop. And of course, that allows us to convert mechanical work into electrical energy. So here, the stronger the magnetic field, the bigger the loop, the more area we have, and the faster the rotation, the greater the EMF is going to be. And that's the basic principle behind a generator.